Today we're going to be talking about factoring polynomials, which as you can see on the slideshow, I call the backbone skill of this course. This lesson is not really part of our curriculum for Math 181, but I take a day and include this because there are so many concepts within this course where factoring polynomials is embedded within it and essential to get to our answers. You have covered this material before in Algebra 1, so hopefully most of this is a review. I am going to show you the methods that I like to use best. Now, this is one of those skills where I don't always necessarily need to see that you do the work, but I need to know that you can do it. So if there is another method that you know and you know you can get to the factors by doing that method, by all means feel free to do that. So let's talk about what factoring is. Factoring is the process of undoing some multiplication. So if we have a product, the factors of that product are the numbers or the terms that we have multiplied together to get that product. So if we think about just numbers, take the number 24. We know that if we take 2 and multiply it by 12, we get 24. So we say that the numbers 2 and 12 are factors of 24. When we think about terms, say we have 2x. Well, 2 and x is what we multiplied to get that term of 2x. So the number 2 and the variable x would be factors. All numbers can be written as factors, including prime numbers. So if we take the number 7, that is prime because it can only be rewritten as factors with 1 and 7. Not all polynomials can be rewritten as factors. There are some polynomials that are considered prime and only one in themselves can be written, so we can't break it down any further, but most of them can. So let's just factor a number. Let's talk about the numbers 12, or the number 12. So if we list out its factors, we've got 1, 2, 3, 4, 6, and 12. That's because we can have the factor pairs of 1 and 12, 2 and 6, and 3 and 4. So all of these numbers are considered to be factors of 12. Now here's the list of factors, here's the factor pairs. We can also do something with numbers that we call prime factorization. Prime factorization means you're making a list of the prime numbers that when you multiply them together, you get the number, in this case, 12. I just sneezed. Excuse me. So when we take the number 12 to prime factor, we're going to make a factor tree. You guys worked with these in early elementary school. You can pick any factor pair besides 1 in itself and break it down. Now when any of the branches of this tree are prime, then that branch cannot be extended any further. So this branch of 2 is prime, so we're going to stop that one. But we can break 6 up into the factors of 2 and 3. Those are both prime. So we say the prime factorization of 12 is 2 times 2 times 3. If you multiply these factors together, which are all prime numbers, you do get 12. Here's factors of 12 over here. Here's the list of factors of 12. And here's the prime factorization. Now let's talk about factoring polynomials. Now there's a lot of different ways to do this. Today we're going to look at 4 of them. We will look at least one more throughout the semester. But what we're going to do, when we say we need to factor a polynomial, we need to take an original polynomial and split it up into the product of other polynomials. Now what does that look like? Well, a polynomial is a mathematical expression containing terms and pluses or minus signs. So if we look at the polynomial x squared plus 2x plus 1. This is what we call a trinomial because it has 3 terms. 1, 2, 3. 2x plus 6. This would be a binomial because it has 2 terms. 2x is a monomial because it has 1 term. Anything greater than 3 terms, we just name it a 4-term polynomial, and so on and so forth. To factor these polynomials, there's many different methods. The method you use is going to be dependent on how many terms the polynomial has, and we go from there. So these are the four methods we're going to use. These are not the official names, it's just what I call them because that's what I use to factor them. Now, some of these are very specific in the form of the polynomial has to look like this in order to use it. I'm going to run through the rules of each of these with you, and then we're going to do some examples. Okay, so the chart method, box method, greatest common factor method, you're going to hear me say those throughout this entire semester. We're going to start with the chart method. Now, in order to do the chart method, your polynomial has to be a trinomial, so it has to have three terms. And in that term, we're going to have a squared term first, and that coefficient, which is the number in front of a variable, is going to be equal to 1. So you're not going to see anything in front of it. So it's going to be a squared term plus or minus the same variable term plus or minus a number. B and C in this form equal numbers. So this is standard form for a polynomial that's going to be factored in chart form. Sometimes these polynomials can be prime, which means they can't be factored, but you're still going to have to try to factor them and figure out if it can be. The only way you can determine a polynomial is prime is if you've exhausted all of the methods and the possibilities for it to be factored. If it can be factored, if it's in this form, squared term plus or minus another variable term plus or minus a number, then if it can be factored, it's going to be factored into two binomial factors. Because our first term is x squared, the only way that x squared can be split up besides one in itself is with an x and an x. So we're going to know what these binomial factors are going to start with. They're going to start with a singular variable of that squared term. To determine what goes behind those x's, this is where the chart comes in. I use this chart to help me determine. I'm going to look for two numbers. I'm going to call those factors. So we're going to find factors of our C term. So numbers that multiply to equal our C term. Those two numbers also have to add to equal our B term. So notice my C comes from here, my B is here. So whatever those two numbers are, we're going to call them M and N, and they can be positive or negative depending on the signs of C and B. Those numbers will complete my binomial factors. Now I know I'm just working with letters right now and that might look a little weird, but we will eventually get to numbers. Okay, so that's the first method, the chart method. It has to be a three-term polynomial in this form. Coefficient is 1 in order to follow these steps for this method. Second method is what I call the box method. Now this isn't always the method that I have used, but it is a method I learned from a colleague when I first started teaching 17 years ago. So I call it the box method because I'm going to use this 4 squared box to help me find my binomial factors. Okay, so again, to do the box method, three terms. Terms have to look like this. The only difference between the box method and the chart method is now there is a coefficient of A. So now we have A, B, and C that are numbers. Now, a lot of you may have learned this method just using guess and check. So you would have split this up. So ax squared splits up, and then c splits up. And you put those into binomials, and you would FOIL or multiply until you figure out which factor actually works. Again, sometimes these are not going to factor, but you still need to check and see if they will. Okay? So, again, my answer is going to look something like this if it factors. To use this box, I'm going to put my ax squared term here and my c term here. Now I need to complete this box, and to do that I am going to go over here and use a chart. Again, I'm going to look for factors, so numbers that multiply, but the numbers have to multiply to give me the product of a times c. Those two numbers still have to add to equal my b value, and I get those still from my original polynomial. Again, I'm going to call those numbers m and n. Once I find the two numbers that multiply to give me the product a and c and add to give me b, those numbers complete my 4 squared box. Now I don't need this chart anymore. Now I'm going to use the rows and the columns of this box to find my binomial factors. Now I'm going to do a couple things before I get started. I'm going to take the sign of this factor and move it up top here. So if it's positive, you put a plus there. If it's negative, you put a minus there. I'm going to do the same thing with this factor, but I'm going to move that sign over here to the side. The next thing I'm going to do is I'm going to split up just the x squared component because I know an x has to go in each factor. Once I do those two things, now I need to find the greatest common factor of the numbers in each column and each row. So columns go up and down. So the greatest common factor of the numbers in this column go up top. Greatest common factor of these numbers goes here, and then you have your first factor. So sitting right here is going to be the greatest common factor of A and Rn. And right here is going to be the greatest common factor of the numbers m and c. That will give you your first binomial term. Then we do the same thing across. Since rows go across, we put those answers to the side here. So in front of this x is going to be the number that represents the greatest common factor of a and m, plus or minus the greatest common factor of n and c. That will be your second binomial term. Again, it looks more confusing with letters. Once we get into examples with numbers, it might make a little bit more sense. The next method is the greatest common factor method. Now, one thing I do want to tell you is that this should be always checked for first. No matter how many terms you have, no matter what form it is in, if your polynomial terms have a greatest common factor that is greater than 1, you always want to take it out. That doesn't mean you're done factoring. You may have to do a little bit more, but always check for this one first. Okay? This method is when we're undoing the distributive property. So if you guys remember the distributive property, that is when you have a number that needs to be multiplied into a polynomial. And in this case, we would get 2x plus 6. So this is our polynomial. This is the factored form of that polynomial. Because we found that between the two terms, 2x and 6, they have a common factor of 2. We took it out in front, and then the factors remaining from each of my terms go in their normal position, first position, second position. So my answer for a greatest common factor factored problem would be GCF on the outside, terms, factors from each term left on the inside. Your answer should look like something you can distribute. Okay. So you're going to hear me ask you every time I ask you to factor something. First question, how many terms? How many terms you have will allow you to eliminate some of our methods. So this one has 3. So right now we could do chart, we could possibly do box, and we always need to check for the GCF. I want to check that first. Okay, so is there a GCF between these 3 terms? So let's erase that. I don't like this question first. I always want to check GCF first. So 1, is there a GCF greater than 1? So in this case, that answer is no, there is not. Between the first 2 terms, I have a GCF of x. Between my last 2 terms, I have a GCF of 4. But I do not have a greatest common factor greater than 1 for all 3 of them. So can't use the GCF. Number 2, how many terms? Well, in this case, it's 3, so chart or box. What is my coefficient of my squared term? It is a 1, so this one is a chart method problem. So if it factors, I know it's going to factor into 2 binomials, and since my first term is 1x squared, I know that has to split up into an x and an x. My job is to figure out what numbers go behind those x's. So remember, I'm looking for numbers that multiply to equal my c value, which is positive 12, and add to equal my b value, which is positive 8. So we've already looked at the factor pairs of 12. So we have 1 and 12, 2 and 6, and 3 and 4. 1 times 12 gives me 12, the product I want, but the sum of those gives me 13. So that's not going to work. 2 times 6 gives me 12. 2 plus 6 gives me 8. So these are the numbers that I want to complete my factors. So they're both positive, so it's going to be a plus 2 and a plus 6 behind my x's. You could also write them like this. Remember that multiplication, you can put in any order and you would get the same answer. And you always want to do a quick check. So if I multiply these binomials, which is the FOIL method, first terms would give me x squared, outside terms gives me 6x, inside terms gives me 2x, my last terms give me 12. That's going to give me the polynomial of x squared plus 8x plus 12. Since this matches what I started with, that tells me these factors are correct. Your factors have to multiply to give you what you started with. Okay, so that's the chart method. The second one, GCF. I've got 10n squared, 43n, and 28. Well, 10 and 28 have factors of 2. N squared and n have a factor of n, but there's nothing that all three of them have in common other than a 1. So I can't use GCF. How many terms? Again, it is 3. So chart, well, I can't do chart because there's a coefficient that is greater than 1. So if this factors, it's going to have to factor using the box method. Okay, I'm going to come down here and rewrite this so I have a little bit more room. 10n squared minus 43n plus 28. So if this factors, it'll factor into two binomials. I can't take a GCF out. So I'm going to make my 4 squared box over here. Your first term goes here. Your last term goes here. And then remember, we are going to multiply a and c. So a is 10, c is 28. So that gives me a product of 280, and it is positive. That's my dog barking. Brutus, stop. So we're looking for two numbers that will multiply to give us positive 280. Those two numbers have to add to give us our b value, which in this case is negative 43. Well, the only way to get a negative sum and a positive product is to have two negative numbers. Negative times a negative will give us a positive, and when we add them, it will give us a negative. So we've got negative 1 and negative 280. That gives me my product, but not my sum. It ends in a 0, so I know I can divide it by 2. That gives me the factors of 2 and 140, but that gives me negative 142. It isn't divisible by 3. It is divisible by 4. I get negative 4, negative 70. That gives me negative 74. It ends in a 0, so I know it's divisible by 5. I get negative 5 and negative 56 as factors. That gives me negative 61. It doesn't divide by 6. It does divide by 7. I get negative 7 and negative 40. That gives me negative 47. I'm getting close. It does divide by 8. I get negative 8 and negative 35. That gives me a sum of negative 43. So these are the numbers that I need to complete my box. Now it doesn't matter where you put them. As long as you have the correct two factors, it will work out. Okay, so remember, before we do anything with the greatest common factors, we want to worry about this. This is negative, so I'm going to slide that up here. This one's negative, I'm going to slide it over here. And then I'm going to take my n squared portion of this box, and I know that n squared has to go in, and n has to go in each factor. Now I can just worry about the greatest common factor of the numbers in the columns and the rows. For some reason, I always start with this column. You can start wherever as long as you put them in the correct spot. So columns go up and down, so my answers are going to go up at the top. Greatest common factor of 10 and 35. Well, 10 has factors of 1, 2, 5, and 10. 35 can divide by 1 and 5. That's it. So 5 is the greatest common factor. 8 and 28. 8 has factors of 1, 2, 4, and 8. 28 can divide by 1, 2, and 4. So 4 would be the greatest common factor. That gives me my first term. Do the same thing across between 10 and 8. The greatest common factor is 2. Greatest common factor of 35 and 28 is 7. Again, if I multiply these out using the FOIL method, I am going to get my original polynomial back. Now, if you want to do guess and check, that's okay. What guess and check would look like is you would just start by splitting up 10n squared. So we could have started with 10n and n. 28, we could have started with 1 and 28. We know this has to be a positive product, but a negative sum, so we know both of those have to be negative, and then we would FOIL. Sorry, this has to be a 28. We know that's not going to work. We could have kept with our 10n and our n, and we could have switched these and go from there. We know that's not going to work. Okay, there are so many. We could have done 4 and 7 and switch that. Here there's so many options that guess and check just takes a long time and you might get frustrated, so I ask you to just try this process. If you are good at factoring and you're okay with this method, that's fine. Like I said, factoring is just something you're going to have to do. Doesn't mean you have to do it my way, but you're going to have to be able to factor polynomials. Let's look at one more example. Okay, now right now this is two terms. We've got 10y squared z cubed minus 15y cubed z. That means we only have two terms. That eliminates chart and box. So right now, the only method we have to use is GCF. Now we know in the GCF we're looking for a greatest common factor to go here. And in this case, since I start with two terms that are separated by a minus, my polynomial factor is going to have two terms in it. Now how do we get to that? We're going to prime factor these. So I'm going to take my terms, I'm going to stack them on top of each other, and I'm going to make my list of my prime factors. So 10, besides 1 and 10, is 2 and 5. Both of those are prime. So that's my prime factors for 10. And then for my variable terms, or variable parts of my term, I'm just going to expand what they mean. So y squared means y times y. Z cubed means z times z times z. If you multiply all of these together, you do get this. I'm going to do the same thing with the second term. Besides 1 and 15, I can use 3 and 5. Those are both prime, so I can't expand any further besides that. So 3 times 5, y cubed is y times y times y, and we have a z. Now I'm able to use these lists to get both parts of my factored term. I'm going to circle the factors they have in common. They have a 5 in common. They have one y in common. They have another y in common, and then they finally have a z in common. Those are the factors they have in common, so I'm going to multiply those. 5 times y times y times z. That gives me the greatest common factor of 5y squared z. That goes out in front for my answer. So if I take those terms out, what is left? Well, in 10y squared z cubed, I've used 5y, y, and z. What is left? I'm left with 2z squared. That goes in the first spot. For the second term, again I used 5, y, y, and z. What is left? 3y. If I multiply 5y squared z times the polynomial 2z squared minus 3y, I get back to this expression. Okay. Now the last method today is what we call the difference of two perfect squares. The title of this tells you exactly what your polynomial has to look like. It has to be two terms, and those two terms have to be perfect squares. and you have to be subtracting them. Now, what does a perfect square look like? When we're talking about numbers, that is any whole number that you square and the product of that. So 2 squared is 4, 3 squared is 9, 4 squared is 16, 25, 36, 49, and so on and so forth. Those numbers are all perfect squares because when I'm looking for what number times itself gives me that, 2, 3, 4, 5, 6, 7, and so on and so forth. When we're talking about variables, we're talking about any variable with an exponent that is even. Square root of x squared is x because x times x gives me x squared. Square root of x to the 6th is x cubed because x cubed times x cubed means I'm multiplying 6 x's together, or x to the 6th. X to the 50th power is a perfect square. Take the square root of it and we get x to the 25th. Because x to the 25th times x to the 25th means I'm multiplying 50 x's together. So some examples of these, start off simple. Let's just start with x to the 4th minus 25. This will always factor into two binomials. The first term will be the square root of a squared, or the square root of this, which equals a. The second term in your binomial factors will be the square root of your second term. Square root of b squared is b. Now, in order to get a negative sign between them, we know we have to be able to multiply a positive and a negative. So your answer will always come out like this. So here, x to the 4th is a perfect square because its exponent is even, and 25 is a perfect square. So the square root of x to the 4th is x squared. That goes here. We know one has to be positive, one has to be negative in order to get a negative product. The square root of 25 is 5. We could make it a little bit more complicated and put a coefficient. So 49x to the 12th minus 121. That would be a perfect square, or difference of two perfect squares. Square root of 49x to the 12th. The square root of 49 is 7. Square root of x to the 12th is x to the 6th. So we get 7x to the 6th as our first term. We know one has to be positive, one has to be negative, and the square root of 121 is 11. Those are the 4 methods for today, okay? Let's run through them. The biggest deciding factor on which method you're going to use is how many terms they have. So say we have a polynomial that has 2 terms. The only methods right now that we know to use to factor them is the GCF or the difference of 2 squares. What if we have 3 terms? Again, we could use GCF, and you always want to check for that first. But you could use chart as long as it is an x squared plus or minus bx plus or minus c term. Remember that x is a variable. It doesn't have to be x. It can be anything. We could use box. Now we put a coefficient in front of that x squared, but everything else remains the same. If we have 4 terms or more, right now we can only use the GCF. So those are the rules that you need to think about when you're deciding which one do I use. Okay, remember that these are not the only ways to factor polynomials in this form. This is what I like the best. You don't necessarily have to use them, but the bottom line is you do have to make sure that you can factor polynomials, because as you'll see in our very first lesson of chapter 1, you're going to have to factor every single problem that we're working with in that section. If you have any questions, let me know. Send me an email, come to my office hours. I will see you soon.